Hello world, we are going to be going over a pretty interesting interview problem using linked lists. So the basic problem statement is that some linked lists have cycles in them where instead of the list coming to an end the way that you would expect where the last element next pointer points to null, it circles back and points to a previous element, so that inevitably will create a cycle where once you get back to that previous element, you just keep working your way forward, and you eventually end up back at that last element, which just points back to the previous one. And if you try to traverse it without worrying about cycles, you could end up in an infinite loop because you'll never reach the end of it. So one interesting thing to note about cycles is they don't necessarily have to come all the way back around to the head. You could have a cycle in a linked list of 10 elements where the 10th element points to the third or fourth element. So the cycle doesn't encompass the entire linked list. It could just go back to halfway through the list, or to like three-quarters of the way through the list, or really anywhere in the list. What makes it a cycle is just the fact that it never really ends, because you just always end up back at a previous element. So the actual problem statement is pretty simple. It's just write a function that will return true if a given linked list has a cycle and false if it does not. So I kind of have like some boilerplate code here already, just to make it easier to test. Um, so don't really worry about any of the code anywhere. The only thing to really notice is this is a singly linked list. So we do have just a next pointer, no previous pointer. And for our solution, that shouldn't really matter too much. There's no point where we would use a previous pointer anyway. And then we have these two functions. One gives us a linked list without a cycle, one gives us one with a cycle. Um, and we can use that to test up here. So this is all just boilerplate stuff to make it easier to test. This is where the fun stuff's going to happen in our has cycle function. So it takes in the head of a linked list, which is a node, and it will return true if it has a cycle. So I recommend at this point, if you haven't thought about this problem very much, pausing and trying to think about it yourself. Um, I will tell you that the most optimal solution, you can actually do it in n time and constant space. There's a significantly simpler one that you can do in n time and n space, but the ideal solution um, is done in constant space. So, um, sorry. So, in order to actually solve this, we have to make use of a technique, um, which is sometimes useful while working with linked lists, and that's called having a runner. So normally when you have a linked list, the way that you'd iterate through it is you'd have your current node, and then you'd say while current is not null, uh, you do stuff to current, and then you iterate current, right? This is the way that we would normally iterate through a linked list. And what this does is it goes one node at a time. It starts at the head and it continues to go one node at a time until it gets to the tail. So a runner is actually just is very similar. The only difference is um, is well, first we want to start it at head.next. We don't want to start it at the same place because we're going to actually have both a current iterator like we have here and a runner. But the main thing that differentiates a runner is it moves two nodes at a time instead of one. And that's sort of the key to actually solving this problem. So, why is that the key? I guess is the question. How is this useful to us? Uh, so, so the main difference is you might have something. Let's go to the iterate step just so you can kind of visualize what a runner and a current, like the difference between a runner and a normal linked list iterator is. Um, so current, we do current equals current dot next. For a runner, we do runner equals runner dot next dot next. Except this is a little dangerous to do because we might have, what if runner dot next is null? Because here we see runners going two at a time. and it's actually going to be ahead of current because it starts ahead of it, and it'll always be ahead of it unless there's a cycle. And at that point, it would go behind it. But if there is no cycle, then it is possible that runner.next is null. So what we have to do when iterating through runner is we have to do it in two separate steps. First, we say runner equals runner.next, and then we'd have to check again and say if runner is not null, then runner equals runner.next. And for our while condition, because runner is always going to be ahead of current, what we want to check is we want to go while runner is not null. Because if runner is not null, then that guarantees us the current isn't. So this is the actual step to iterate through the list with one current node and one runner. So the current goes 2 at a time, the runner goes 1 at a time. So if you think about it, we can actually use just these 2 nodes, not having to store anything else, to tell whether there's a cycle in the list. Because first, let's consider the case where there isn't a cycle. So if there's no cycle, then we iterate through the list. The idea is that once we get to the very end, we can return false, because if runner equals null at some point, that means it made it to the end of the list. There is a point where the next pointer is null. So there's obviously no cycle if there's a point where there's no next element. One of the characteristics of a cycle is that every node's dot next points to another node. So that's why this works for when there is no cycle, is because eventually this will become false. So now we have to think, in which case we return true. So if there is a cycle, we could, given the code we have right now, iterate forever. We could get stuck in an infinite loop, and that would be bad. So let's think about what we need to check for. So if this is our list, let's say we have elements 1, 2, 3, 4, 5, and then let's say it cycles back around to 2. And this is just because I can't draw well using ASCII art, but pretend that this is actually just a pointer back to this element here. So if there's a cycle, let's make it a little bit smaller, just make it easier to work with. So we have elements 1, 2, 3, and then 3 points back to 2. And of course this 2, the 3 points back to this 2, and this 2 points to this 3, and this 3 points back to this 2. So there's our cycle. And so if we just go through this algorithm, we end up with current starts pointing to here and runner starts pointing to here, right? So just remember that this points back to 2. So current starts here, runner starts here. So on the first step, runner will iterate twice. So it'll go to 3, and then from 3, it'll iterate back to 2, because remember, that's just the cycle the way we defined it. And current goes forward 1. So we end up in a case where current and runner are both pointing to the same element. And this happens if and only if there is a cycle. That at some point they point back to the same element. It's not always necessarily after one step. In fact, it very rarely is. If we instead made it 4 elements long and the 4th element points back to 2, we'd start with current here and runner here before our first step. And then after our first step, current would move up by 1, so current would move up to here, and then runner would move up by 2, so runner would move up to here. And then on our second step, current would move up by 1, so current would move to 3, and runner would move up by 2, so it would move from 4 to 2, because remember 4 cycles back to 2, and then to 3. So they'd both be on the same element. And this happens every single time, because there's no real way, because we know runner's moving faster than current, so it will eventually catch up to it. And because runner and current both move at the same time, there's no scenario where runner could hop over current. So that's why this works. So we're basically just checking to see if runner and current are ever equal, then we can return true. So we also want to make sure we're comparing the actual values and not the data that's stored within them. So here we have runner and here we have current, if they're equal. So this comparison is comparing their pointers. It's comparing their their address in memory. You want to be sure not to do runner.data equals current.data because you could have multiple elements in the list that have the same data. So here we're just comparing where they exist in memory. So if runner equals current, that means that we do have a cycle, so we can return true. And this is actually really all there is to it. Um, so, so if we don't have a cycle, this will never be true because runner is always ahead of current, and we'll eventually get to the point where runner is null um, at the very end of the list, and we will return false. Now, if there is a cycle, this will always eventually become true because runner will catch up to current um, eventually. That's absolutely guaranteed. Runner's moving faster, and there's no way for a runner to overtake current. And it'll do it in at most 2 n steps, which is why we still have that n time algorithm. So this is really the entire algorithm. Hopefully that makes some sense. We can go ahead and run this example now. So let's start with a linked list that has no cycle. Actually, before we run it, just to make it a little easier to visualize, let's print out the values for current and runner, just to make it a little easier to see like, what's actually happening. So there's our current and there's our runner. And if you look at the list, these are both just lists. Linked list with a cycle goes from 1, 2, 3, then back to head. So the entire list is a cycle counting 1, 2, 3, 1, 2, 3. And the one without the cycle is just 1, 2, 3, but the last node points to null. So let's go ahead and run this with no cycles. So this is the one that's just 1, 2, 3, and then it ends. So let's see what things are pointing to. Oh, so this one actually only takes 1 step because here we see current is 1 and runner is 2. Remember, runner will always start 1 ahead of current. And then after the very first step, runner goes to runner.next, which is 3, and then that's not null, so then that goes to runner.next. So here runner becomes null. So our loop sees the runner is null, which means we have reached the end of the list, meaning there can't be a cycle. So we exit out and we return false, which is perfect. That's exactly what we were expecting. Now let's try it with cycle. So this is the more interesting case. Cool. So let's see what happens here. So on our first step, same thing. Current points to runner points to 2. On our second step, current now points to 2 because current went from 1 to 2. That seems perfectly fair. Meanwhile, runner went from 2 to 1. So runner went 2, then to 3, then, because it has a cycle, from 3 it went to 1. So this is after a second iteration. And now for our third iteration, current went from 2 to 3, and runner skipped 2 and went from 1 to 3. So, so we check, we see that they're pointing to the same element, and therefore we return true. And that is how you can find a cycle without using any extra data structures. And you can do it in n time, which is pretty cool. All right, I hope you enjoyed this video, and I hope it's useful for you.